Curvature, the unity of gravity and acceleration. There was a time when gravity was thought to be a silent puppeteer, an invisible force reaching across space, pulling objects together with an unquestioned authority. From the falling apple to the orbiting moon, everything seemed to obey this mysterious attraction described so elegantly by Isaac Newton. And yet, beneath this elegance, there lingered a quiet discomfort, a question that refused to rest. What is gravity truly? Now imagine, if you will, a simple scene. You are enclosed within a perfectly sealed box, no windows, no doors, no clues of the outside world. Suddenly, you feel a force pressing you firmly against the floor. Your feet grow heavy, your body anchored. Instinctively, you might say, "Ah, I am standing on the earth. Gravity is pulling me downward." But let us disturb this certainty. What if, instead, this box is not resting on any planet at all? What if it is far removed from stars and galaxies, drifting in the emptiness of space? And what if, unbeknownst to you, the box is being pulled upward by a rocket, accelerating steadily with an acceleration we may call A? The force you feel pressing you to the floor is no longer gravity. It is the result of acceleration. And here lies the astonishing revelation. Your experience inside the box would be exactly the same in both cases. To understand this more deeply, let us give form to these ideas. When you stand on the surface of the Earth, you experience what we call gravitational acceleration, commonly described as g is approximately equal to 9.8 meters per second squared. This means that if you were to drop an object, it would accelerate downward at this rate. Your weight, the very sensation of heaviness, arises because the ground prevents you from freely falling under this acceleration. Now consider the accelerating box in space. If the rocket pulls the box upward with an acceleration equal to g, then every object inside, yourself included, will be pressed against the floor with a force indistinguishable from gravity. The equations describing motion in both cases become identical. In fact, according to Newton's second law, force is equal to mass multiplied by acceleration. The force you feel depends on your mass and the acceleration. Whether this acceleration is caused by gravity or by a rocket engine is, from your local perspective, entirely irrelevant. This is not merely a coincidence, it is a profound statement about the nature of reality. Let us push this thought experiment further. Suppose you release a ball from your hand inside the box. In the case where the box rests on Earth, the ball falls toward the floor due to gravity. In the accelerating box, however, something subtler occurs. As the box accelerates upward, the floor rises to meet the ball. To you, the observer, the ball appears to fall in precisely the same way. The trajectory, the timing, the motion, all are identical. You cannot, by any experiment confined within this small space, determine whether you are in a gravitational field or in an accelerating frame. This is the essence of the equivalence principle. Gravity and acceleration are locally indistinguishable. But notice the word locally. It is a whisper of caution, a boundary to this truth. If your box were large enough, you might detect subtle differences, tidal effects, variations in gravitational strength from one point to another, but within a sufficiently small region, these differences vanish into insignificance. Reality becomes beautifully ambiguous, and here the world begins to shift. For if gravity can be mimicked perfectly by acceleration, then perhaps gravity is not a force in the traditional sense at all. Perhaps it is not something that pulls, but something that guides. Perhaps what we call gravity is simply the natural motion of objects in a world where the stage itself, space and time, has been quietly reshaped. This realization did not come easily, even to Albert Einstein. It required a leap of imagination, a willingness to question the very foundation of classical thought. Yet once seen, it becomes impossible to ignore. The distinction between being pulled and being accelerated dissolves, leaving behind a deeper unity. In this unity, the universe reveals a subtle elegance, the same mathematics, the same experiences, the same physical laws arise from two seemingly different causes. Gravity and acceleration are not separate actors, but two faces of the same underlying reality. And so, what began as a simple question, what is gravity, leads us to a profound answer. It is not merely a force, but a reflection of how motion itself is defined. In the quiet confines of a falling box or an accelerating rocket, the universe whispers its secret. There is no fundamental difference between falling freely and floating weightlessly in deep space, save for the perspective from which you observe it. The universality of free fall. There is something almost poetic about the way objects fall. A stone released from the hand, a feather drifting in still air, a planet tracing its path around a star, all are participants in a silent choreography governed by gravity. And yet, for centuries, it was believed that this dance was unequal, that heavier objects must fall faster, that weight itself dictated the urgency of descent. This belief, though intuitive, was gently but firmly challenged by Galileo Galilei. Legend tells us that he climbed the leaning tower of Pisa and released two objects of different masses, watching as they struck the ground together. Whether or not the story unfolded exactly so, the truth it conveys is undeniable. All objects fall at the same rate when the influence of air resistance is removed. This is the universality of free fall, a principle so simple in its statement, yet so profound in its implications. Let us begin with the familiar expression for gravitational force as given by Isaac Newton. The gravitational force between two masses is equal to the gravitational constant, multiplied by the product of the two masses divided by the square of the distance between their centers. Here, the force depends on the mass of the Earth, the mass of the falling object, and the distance between them. At first glance, this equation seems to suggest that heavier objects should experience a greater force and thus fall faster. But nature, as it often does, hides its simplicity behind apparent complexity. To uncover the truth, we must turn to another cornerstone of physics, Newton's second law of motion. Force is equal to mass multiplied by acceleration. Now, if we consider a falling object, the gravitational force acting on it must equal the force described by this second law. Therefore, we may write that mass multiplied by acceleration is equal to the gravitational constant times the Earth's mass times the object's mass divided by the square of the distance. Now comes the quiet miracle. The mass of the object, which appears on both sides of the equation, cancels out completely. What remains is that the acceleration of the falling object is equal to the gravitational constant multiplied by the Earth's mass divided by the square of the distance. Notice what has happened. The acceleration of the falling object no longer depends on its own mass. Whether the object is a stone, a coin, or a cannonball, its acceleration toward the Earth is exactly the same, determined only by the mass of the Earth and the distance from its center. This is not merely a mathematical curiosity, it is a statement about the deep symmetry of the universe. But to fully appreciate this, we must distinguish between two concepts that, at first glance, seem identical. The first is inertial mass, the measure of an object's resistance to acceleration. It appears in the equation describing force equals mass times acceleration. The second is gravitational mass, the measure of how strongly an object interacts with a gravitational field. There is no obvious reason why these two masses should be the same. One governs how an object responds to force, the other governs how it experiences gravity, and yet in every experiment ever performed, they are found to be equal. It is this equality that allows the mass to cancel in our equation. It is this equality that ensures all objects fall in the same way. To say it differently, the reason all objects fall with the same acceleration is because inertial mass and gravitational mass are exactly equivalent. This realization is not trivial. It is, in fact, one of the deepest clues nature offers us. Imagine once again our sealed box floating somewhere in the vast emptiness. If you release two objects of different masses inside it, they will simply hover, drifting side by side. But now place this box in a gravitational field or accelerate it upward. Release the same two objects, and you will observe that they fall together, maintaining their relative positions as they descend toward the floor. No matter how carefully you observe, no matter how precisely you measure, you will find no difference in their motion due to their mass. The universe refuses to distinguish between them. Even more striking is what happens in the absence of air resistance. On the surface of the moon, where there is no atmosphere to interfere, an astronaut once dropped a hammer and a feather. They fell together, touching the lunar ground at the same moment, a quiet, beautiful confirmation of this principle. And so we are led to a remarkable conclusion. Gravity does not pull harder on heavier objects in any meaningful sense. Instead, it shapes motion in a way that is completely independent of the object's nature. Every object, regardless of its composition or mass, responds to gravity in precisely the same way. This universality hints at something deeper still. If gravity treats all objects equally, perhaps it is not a force acting upon them in the usual sense. Perhaps it is something more fundamental, a property of the space through which they move. Indeed, this idea would later guide Albert Einstein toward a revolutionary insight that gravity is not a force at all, but a manifestation of the geometry of space-time itself. But even before we arrive at such heights, we may pause and reflect on the elegance of what we have uncovered. The falling of objects, so ordinary, so easily overlooked, reveals a hidden unity. The stone and the feather, the planet and the star, all follow the same silent law, and in this law, the universe whispers a profound truth. In the presence of gravity, all differences of mass are, in a sense, illusions. What remains is motion itself, guided by a deeper order that binds all things equally. Gravity as geometry, not force. For centuries, gravity was imagined as an invisible thread, an unseen hand reaching across the void, pulling objects toward one another with unwavering obedience. In the grand formulation of Isaac Newton, this idea found its most precise expression. The gravitational force between two masses is equal to the gravitational constant multiplied by the product of their masses, divided by the square of the distance between them. Here, gravity appears as a force, a direct interaction between masses, diminishing with distance in a precise mathematical way. It is elegant, predictive, and extraordinarily successful. And yet, if one listens carefully, there is something almost unsettling about it. How does one object reach out across empty space to influence another? What medium carries this force? What mechanism enforces this silent connection? These questions lingered like faint echoes, unresolved. Now, let us return to the insight born from the equivalence principle, the idea that gravity and acceleration are locally indistinguishable. This simple yet profound statement begins to erode the very foundation of gravity as a force. For if the effects of gravity can be replicated entirely by acceleration, then perhaps what we perceive as a force is merely a reflection of how motion unfolds within a deeper structure. To see this, imagine once again our sealed box. But now, instead of resting on Earth or accelerating in empty space, let it fall freely under gravity. The moment it begins to fall, something remarkable happens. The sensation of weight disappears. Objects inside the box float as if gravity itself has vanished. This is not because gravity has ceased to exist, but because everything within the box is falling together. There is no relative acceleration between objects. No forces are felt. The experience is identical to drifting in the emptiness of space. In this freely falling frame, the laws of physics take on their simplest form, the form described by special relativity. Motion proceeds as though space and time themselves are guiding it effortlessly. And here, a new idea begins to emerge. Perhaps objects are not being pulled by gravity at all. Perhaps they are simply following the natural paths available to them, paths determined not by forces, but by the very shape of the stage upon which they move. To express this idea, we must introduce a new language. not the language of forces, but of geometry. In this language, the motion of an object is described by what is called a geodesic, the straightest possible path in a curved spacetime. In flat space, this reduces to a straight line, but in curved spacetime, straight is no longer obvious. It is defined by the geometry itself. Mathematically, this idea is captured by the geodesic equation, which states that the change in motion of an object plus a curvature-dependent term involving the Christoffel symbols acting on its velocity is equal to zero. What this tells us is profound. An object moves in such a way that its path is determined entirely by the geometry of spacetime. There is no force term here, no push, no pull, only motion guided by curvature. To understand this intuitively, imagine placing a heavy ball on a stretched rubber sheet. The ball causes the sheet to curve, creating a depression. Now roll a smaller ball across the surface. Its path will bend, not because an invisible force is pulling it, but because the surface itself is curved. This analogy, though imperfect, offers a glimpse into the truth. Mass and energy tell spacetime how to curve, and curved spacetime tells objects how to move. This relationship is expressed in its full glory by the field equations of Albert Einstein. The curvature of spacetime is proportional to the distribution of mass and energy in the universe. Here, gravity is no longer a force. It is the very curvature of reality itself. The falling apple does not accelerate because it is pulled by the earth. It accelerates because it is following the straightest possible path in a space-time that has been curved by the Earth's mass. The orbiting planet does not circle the sun because of a tugging force, but because it is tracing a natural path through a curved geometric landscape. This shift in perspective is not merely a refinement, it is a revolution. It replaces the notion of action at a distance with a local geometric description. It transforms gravity from a force into a property of space-time itself, and perhaps most beautifully, it unifies motion and geometry into a single, coherent vision. Objects move as they do because space-time is as it is. There is a certain elegance in this idea, a quiet harmony. The universe no longer requires invisible threads or mysterious forces. Instead, it unfolds according to the shape of its own fabric. Thus, what we once called gravity reveals itself as something far more profound, not a force acting within space-time, but the very structure of space-time itself, the local nature of physical laws. There is a subtle and almost paradoxical truth hidden within the equivalence principle, a truth that whispers rather than declares itself. It tells us that no matter how vast and curved the universe may be, no matter how strong the pull of gravity, there always exists a small enough region where the laws of physics return to a simpler form, as if gravity had quietly stepped aside. To appreciate this, we must first recall the elegant structure of special relativity introduced by Albert Einstein. In that theory, the geometry of space-time is flat, and the motion of objects follows the simplest possible rule. In the absence of forces, they move in straight lines at constant velocity. This idea is encoded in the invariant space-time interval. The space-time interval between two events is equal to minus the speed of light squared multiplied by the time difference squared plus the square of the spatial separations in the three directions. This equation defines a flat geometry, unchanging, uniform, and free from the distortions of gravity. But our universe, as we now understand, is not flat on large scales. It is curved by the presence of mass and energy. This curvature is described by a more general expression. The space-time interval is given by the metric tensor multiplied by infinitesimal changes in space-time coordinates. In this equation, the metric tensor encodes the geometry of space-time itself. Unlike the flat case, where the structure is fixed and simple, here the geometry can vary from point to point, bending and stretching in response to the presence of matter. At first glance, this seems to complicate everything, If space-time is curved, then surely the laws of physics must also become more complex, tangled in the distortions of gravity, and yet the equivalence principle offers a remarkable reassurance. It tells us that at any given point in space-time, it is always possible to choose a local frame of reference in which the effects of gravity disappear. Let us make this more concrete. Imagine once again a small laboratory, perhaps no larger than a modest room, falling freely under gravity. Inside this laboratory, objects float weightlessly. A dropped object does not accelerate toward the floor. Instead, it drifts gently, as though gravity were absent. In such a frame, the geometry of space-time simplifies. The metric tensor, which may vary across large distances, can be approximated locally as the flat Minkowski metric of special relativity. In other words, within this small region, spacetime behaves as though it were perfectly flat. This is not a global statement, it is a local one. Over larger distances, the curvature becomes apparent again. But within a sufficiently small neighborhood, the complexity fades and the familiar laws of special relativity re-emerge. Even more striking is what happens to the motion of objects. Recall the geodesic equation, which governs motion in curved spacetime, the second derivative of position with respect to proper time plus curvature-dependent terms involving the Christoffel symbols acting on velocity equals zero. The Christoffel symbols, which encode the effects of curvature, can be made to vanish at a single point by an appropriate choice of coordinates. In this special frame, the equation reduces to simple uniform motion with zero acceleration. Once again, gravity has been transformed away, not by removing it from the universe, but by choosing a frame in which its effects are not felt locally. This idea carries profound implications. It tells us that gravity is fundamentally different from other forces. An electric field, for example, cannot be eliminated by simply changing one's frame of reference. It persists, measurable and undeniable. But gravity, at least locally, can always be made to disappear. This is why we say that gravity is not a force in the traditional sense. It is not something that acts within space-time, but something that shapes space-time itself. And because of this, its effects can be removed locally by choosing a freely falling frame. Yet, there is a delicate nuance here. While the effects of gravity can be eliminated at a point, they cannot be removed over extended regions. If our laboratory were large enough, we would begin to notice subtle differences. Two objects released at slightly different positions might drift toward or away from each other. These are tidal effects, signatures of space-time curvature that cannot be transformed away. Thus, the equivalence principle draws a boundary. Locally, the laws of physics reduce to those of special relativity. Globally, the curvature of space-time reveals itself. There is a quiet beauty in this idea. It suggests that no matter how complex the universe becomes, there is always a small enough scale where simplicity is restored. It is as though nature carries within itself a principle of clarity, ensuring that even in the presence of gravity, the fundamental laws remain accessible. And so, when we speak of the local nature of physical laws, we are speaking of a profound harmony. The universe may be curved, dynamic, and vast beyond comprehension, but at every point it offers a window into simplicity, a place where the laws of physics take their most elegant form. In this way, the equivalence principle does more than unify gravity and acceleration. It reveals a deep structure within reality itself. That complexity and simplicity are not opposites, but reflections of scale, and that at the smallest scales, the universe always returns to its most fundamental truths.